series and look at a few other examples. And I've got some sample questions from a past exam paper as well. I thought we might have a look at and have a go at in this session. Just a very quick recap on what I did yesterday. So I saw you yesterday morning. So what did we do then? Well, yesterday morning we finished off looking at the convergence test. And we began with the alternating series test. And this told us, so alternating series are series which are alternatively positive and negative. And we looked, there's a nice clear condition for the convergence of those series. That is, if it's an alternating series and the absolute values of the terms, which would be the AMs there in the statement of the theorem, theorem 2.8, if those are decreasing and converging to 0, then the series is convergent. And we just gave an informal explanation for this, because if you look at the evolution of the partial sums of that series, if the AM are decreasing and converging to 0, then the partial sums are stepping up with each positive term, then they step down with a negative term, then they step up again and step down. So they're zigzagging up and down. And the step size each time, the size of the step each time is the absolute value of AM, and the steps are alternatively up and down. But if those step sizes are decreasing and converging to 0, then, in fact, all they need to be is converging to 0, I think. Yeah, all they need to be is converging to 0. Then the partial sums are going to be changing less and less each time, and so they're going to be zeroing in on some convergent limit. And that's not a rigorous proof, but it's just a kind of a motivation. It gets across the essential idea behind the proof. To prove it formally, you'd need to go back to an epsilon argument and possibly using the comparison tests as well. Then we looked at two tests, the ratio test and the root test, and these were both combinations of the comparison test and the geometric series test. This gives us two ways of detecting when series were behaving approximately like a geometric series. And if the series you're examining is behaving approximately like a geometric series, then whatever the behavior of the corresponding geometric series, if that's convergent, so will the series you're looking at be. Whereas if the comparison geometric series is diverging, then so will the series you're examining. Okay? So the ratio test worked by forming the ratio of consecutive terms of the series and taking the limit of that. It gives you a limit L. If the L is less than 1, it means it's approximately like a geometric series with constant multiple less than 1. So that will be a convergent one. If it's greater than 1, it's going to be a divergent. There's one unresolved case. If L is equal to 1, the ratio test fails to give a conclusion. Okay? So the test could still be convergent or divergent. You wouldn't know from the ratio test. The root test, again, compares to the geometric series test, and this operates by taking the nth root of the nth term of the series. So this is appropriate when the terms of the series have some kind of, have the summation index m or some simple function of it appearing in the exponent position of the terms. Okay? So we looked at some examples of that. And again, so you get that limit of the nth root of the nth terms, and then the conclusion is based, the conclusion operates the same way as in the ratio test. If it's less than 1, it's convergent series, and if it's strictly greater than 1, it's going to be a divergent series. Again, the L equals 1 case is unresolved. Okay. So I think mainly like to spend the time now this afternoon doing some examples, but we'll just quickly look at an important class of series. Now we'll be coming back to these. These are called power series. We'll be coming back to these when we're doing the calculus in term 2, when we're looking at the derivatives of real value functions. Because that's really the appropriate place where we should study these, because these series, well, the main ingredient in them is the concept of the derivative of the function. Okay? But because they're an important class of series, I just want to introduce them now and just familiarize you with the notation and just the kind of look and feel of them. These are called power series. So a power series is a function. So it's a function defined by a series. So the general appearance of it would be some function a of x. So x is the argument of the function, and the way the function is defined is as a, well, here as an infinite series. Now, of course, that's only a sensible definition of a function in the case where the series converges. Okay, but it's a different series for every different value of x you put in. So for some values of x, it might converge. For some values of x, it might diverge. So power series have this feature that they may not be well defined. They may not; those series expressions may not give a valid definition of the function for the whole range of x, for the whole domain of the real numbers. It may only be partially applicable, and it's actually an application of the ratio test that describes that. So if we apply the ratio test, which is what's done here, if you take this series, and it now has a parameter x in it, so the AMs are the terms, or the coefficients, if you like, and it now has this parameter x in it. And of course, the x is raised to the power n, so it's like an infinite polynomial in x. Yeah, you should probably change that summation so it begins at 0, actually. Power series should have the ability to have a constant term in the front of them. So if you change that summation to begin at 0, I was a bit careless there. So you would have a constant term, a0 is the first term, then you'll have an a1x plus a2x squared plus a3x cubed plus a4x to the power 4 and so on. So it's like an infinite polynomial. Now, when might such a thing converge? Well, if we apply the ratio test, that's what's done here, the only time that series is going to converge is when the limit of this ratio stuff here is strictly less than 1. Okay, so you take the m plus 1th term of the power series, which is am plus 1 times x to the power m plus 1, and divided by am times x to the power m. So we're looking for when that is less than 1. Now, that will depend on what the value of x is, okay? Because the limit of this ratio, so the AMs are kind of known, or fixed quantities, fixed coefficients, but the x is a parameter, is a variable. So for some values of x, that limit might be 1, and for some values of x, it might not be. Now, what we notice is that we've got what you've got written there is the limit of am plus 1 x to the power m plus 1 over am x to the power m, strictly less than 1. But now the thing is, this is the limit as m goes to infinity. But of course, you can immediately cancel the x's here. So this is the limit as m goes to infinity, and this is am plus 1, and you're just left with an x on top divided by am. Okay, so you've m plus x to the power m plus 1 on the top, x to the power m on the bottom. So this is the question, is it less than 1? Is the question. Well, this is equivalent now to the question that is the absolute value of x times this limit m to infinity of am plus 1 over am, is this strictly less than 1? Now what have I done there? We've taken the x outside the limit operation. We can do that because as it stands here, we're taking the limit as m goes to infinity, but x has no dependence on m. X is just the variable or the argument of the power series. But there it is, sitting in the middle, sitting underneath the limit sign, sitting in the scope of the limit sign in the second last equation. But x doesn't depend on m, it's independent of m. So it's just acting like a constant in the middle of this ratio here. The other parts of the ratio do indeed depend on m, am plus 1 and am, so they have to stay there under the scope of the limit operation. But this x can move out. So you just send the x outside, factorize it out, and it comes out to the front. And then that gives you the expression that we end up with in the notes. So we can divide, if this limit exists, we can bring it over to the other side. So it's like dividing both sides by the limit. So it'll be the limit of the reciprocal of these things. So the am over am plus 1. Okay, so you have to invert it because you're bringing it over to the other side. So if this limit exists, and if absolute value of x is less than it, then the series is going to be convergent by the ratio test. So if the answer, these are questions here, equivalent questions, if the answer is yes, then a of x converges. That's the conclusion. So this limit then is very important. This limit on the right-hand side, okay? And it's called the radius of convergence.
Is that limit is
M. So x, yeah, crikey. Yeah, that was a moment of madness. M goes to infinity. Okay. So this limit gets called R. This limit is called R, called the radius of convergence. It's discussed there. So in general, this is the feature that the power series converges inside here, converges here, but diverges outside. So there's a neighborhood around 0 where the power series will converge. Now, sometimes this limit here, sometimes R is equal to infinity, that this limit is unbounded. In which case, the power series converges. It makes sense. It's a valid function over the whole of the number line. Other times, though, this limit comes out as being a finite quantity. Now, it's called the radius because in general, well, I mean, R here this is a one-dimensional circle you're looking at, just 2 points equidistant from the origin on the line. That's a one-dimensional circle. Two-dimensional circle, of course, is drawn in 2 dimensions, circle of points around the origin. I mean, we normally use the term radius for this kind of thing. And a main application of power series is in functions of 2 variables, functions defined in the complex plane, complex numbers, and there the radius of convergence is an actual radius of a circle. But in general, we could consider this a one-dimensional radius. This is a one-dimensional circle you're looking at there. Okay. Now, where do these power series come from? And this is the link to differentiation. What are these coefficients am? Well, in general, they're going to be the derivatives of the function, or the evaluation of the derivatives of the function at some base point. Okay. So the main discussion of this will postpone till the calculus chapter. But let's just look at this simplified expression here. When we're basing them around 0, so when it's fitting into this picture here, that we're talking about the behavior of the function centered at 0, then this is the appearance of what those power series look like. So it's going to be a infinite series for a function f. You recognize that as an infinite polynomial because it's the sum of these terms x to the power n, and n is going from 0 up to infinity. And the coefficients multiplying it are these quantities here, f, and with n in the superscript in brackets. So that refers to the nth derivative. The 0th derivative of f is just the function f itself. The first derivative of f is the first derivative. The second, f superscript brackets 2 will be the second derivative. So now we'll come back to this in much more detail when we're doing differentiation in term 2, and we'll kind of give arguments to justify why this happens and why this is the case. Okay. when we understand more about the derivative. Okay. Well, we can have a look now, and just to get a feel for it, a taste for it. Here are some common power series. In general, these are called Taylor series, but when they're centered at 0, they often have the special name Maclaurin series. Various names that are attached to them. But they're all examples of power series. So these are some common familiar functions here. An exponential, trigonometric function, sine and cosine. This kind of a reciprocal function, 1 over 1 minus x, which is a particularly nice, simple Maclaurin series. All the coefficients of x to the power k are 1. And then here's the logarithm function as well. Okay. Now these are useful tools. You see, although they're infinite series, the idea is if you take a partial sum of that infinite series, then you have an approximation to the function in question. Okay? So if you're happy with dealing with approximate values for these functions, all you need to do is just take an appropriate partial sum of these infinite series. And the longer the partial sum you take, the more terms you include, the better and better the power series approximates the given function. Okay? And power series like this and other related mathematical objects, they're the things that actually allow us to evaluate these functions with computers and so on. I won't say it's exactly these formulas that are being applied when you ask the computer to evaluate them, but in some cases it will be, or in other cases it will be kind of related approximating polynomials. So if you think about it, you're well used to typing into your calculator, give me sine of 22.34 degrees or something. How is it that the calculator is able to tell you what that is? And the calculator doesn't know anything about triangles. Right? And even our sophisticated computers, they don't really know anything about triangles or about what the logarithm function is representing and so on. I mean, fundamentally, computers, all they can really do is just add stuff together, really. In fact, fundamentally, all the computer can do is just add 1 and 0 together. It can add 1 and 0 together and say that's equal to 1. It can add 0 plus 0, say that's 0. And it can add 1 plus 1, and it knows that that's equal to 0. Well, it's equal to 1, 0 in binary, 10 in binary, which represents 2. At the fundamental level, that's really all computers can do. And everything else is just built on top of that. So once you can add single bits together, 0s and 1s, you can extend that to adding any numbers, which you can represent in binary. If you can add numbers together, you just extend that, build on that. It means you can multiply numbers, because multiplication is just repeated addition and so on. So at the bottom level, all the computers can do is just add stuff together. Multiplication is built on top of that. But that's enough to evaluate approximating polynomials like the partial sums of these power series. Because what's involved in evaluating a polynomial? See, the polynomial terms are x raised to some power, but that's just multiplication of x, multiplying x by itself a certain number of times. Then you multiply it by a certain coefficient, and then you add all those parts up as described by the series, or the partial sum. So those fundamental operations in evaluating a polynomial of addition and multiplication, those can be carried out by the circuitry of the computer. So power series like this, in some cases, but in practice, probably most of the time, other more specialized approximating polynomials, those are the things that actually allow our computers and calculators to evaluate these arbitrary functions and allow us to compute them. Okay? So they're very important. You'll also see them occur in later units when you're looking at the numerical solutions of differential equations in your second and third years and partial differential equations. Very often we use approximating techniques, which a lot of them are based on this idea of using a Taylor series and power series. Okay. Well, this is just kind of like a first glance at them. And we'll return to them in more detail in term 2. Okay. Okay. So I'd like to finish off with a few examples of some other things with series which I haven't covered with you yet. So the first one is going to be an example showing. Now, some of you may have covered this in one of your tutorials. You may have seen this in one of your tutorials, or you may not. But this is an example showing telescoping behavior of the partial sums. So this is an interesting technique which can sometimes allow you to evaluate the value of a series. So what we're going to do is we're going to consider this example, which is the sum of 1 over n times n plus 1 from n equals 1 to infinity. So we're going to look at this sum and try and figure out what it should be. And the way we're going to figure out what this infinite series is, well, it's using the definition. Using the definition for the limit of an infinite series, and that's using the partial sums. Okay? But first of all, we observe there's a different representation for 1 over n times n plus 1. This is called a partial fraction representation. So 1 over n times n plus 1, what you can do, because the denominator factorizes like that, and again, this is something we'll deal with in detail in a later chapter on functions. We'll look at partial fraction technique in general. But for this straightforward example, what we seek to do is to express this single fraction as a sum of two fractions. One with each factor of the denominator from the original fraction. Now, if you think about how these, what you have to rely on here is the meaning of adding two symbolic fractions together. Well, if you want to add these two fractions together, you multiply the denominators to give you a common denominator, and you re-express each of these two fractions over the new denominator, and then add the numerators. Okay, so you think back to what it means to add together symbolic fractions like that, or add together any fractions. But we see that if we have the coefficients 1 and minus 1 on this, when you add these fractions together, you do indeed get this original fraction. And then we look at the partial sums. So now we'll look at a partial sum, sk. So sk, by definition, is the sum from n equals 1, not up to infinity, but just going up as far as k. So we're going to look at this partial sum of the series, but now we have a different representation for it as 1 over n minus 1 over n plus 1. What happens to this when you add it up? See, these two fractions are very similar. One is 1 over n, the other one is minus 1 over n plus 1. So they're very closely related. And we're adding them up for successive values of 1. But what you see is, like, every time you get a minus 1 over n plus 1, when n increases to the next value, you're going to get that same fraction but with a positive sign here. So you're going to see these fractions repeated all over the place, sometimes half the time with positive signs, half the time with negative signs. So you're going to get a lot of cancellation. Now, you can track what's happening there if you expand out the summation a bit and just look at what's happening, and you'll see the kind of pattern. I mean, when n is 1, you've got 1 minus a half. When n is 2, you've got a half minus a third. When n is 3, you've got a third minus a quarter. Okay, so you keep on adding these. There's a dot, dot, dot here. Let's add in the last 2. So the second last term of the partial sum is when n is equal to k minus 1. So there you'll have 1 over k minus 1 minus 1 over k. Then the very last term is when n is actually equal to k. So the last term is 1 over k minus 1 over k plus 1. Now most of the fractions there are repeated twice. Or most of the fractions in that expression occur twice. Once with a positive sign and once with a negative sign. So most of them cancel. This minus a half cancels with plus a half. This minus a third cancels with plus a third. This minus a quarter will cancel with the plus a quarter, which is going to follow it. I haven't written it in, but it does. In the same way, this see, each negative thing cancels with its positive partner, which comes after it. So this positive partner plus 1 over k minus 1, that's going to cancel with its negative partner that came once before. This minus 1 over k cancels with that minus 1. So this negative one at the end, this does not cancel, because there is no positive partner following it. The negatives cancel with their positive partner, which follows. But this last negative, there is no positive partner. In the same way, this one at the beginning, each positive thing is cancelled by the negative thing that came before it. This one at the beginning, there is nothing that came before it, because it's the very first thing. So there's nothing that cancels that one. So this expression immediately simplifies to this 1 minus 1 over k. Now this is a very simple, a very compact, completely understandable expression for the partial sum sk. Normally, we think of the partial sums have these dot, dot, dots in them. You're just adding up some kind of expression for increasing values of the index. Normally, for an arbitrary expression, it's normally not possible to get a nice compact formula. But for this special case, we can. And remember, what does the sum of an infinite series mean? How is it defined? By definition, this is the limit of the sequence of partial sums. Okay? That's the definition in the very start of the series chapter. That's the definition that we attach to an infinite sum. Okay, so initially, the concept of an infinite sum doesn't make sense if you think of it as a mechanical, time-based operation of adding things together, because you can never finish it. There's an infinite number of things to add up. But we did interpret it in a meaningful way using our knowledge of sequences. So we'd already talked about sequences and how we can talk about limits of sequences. But this is how we defined the sum of an infinite series. But we have this nice expression now for sk, which is just 1 minus 1 over k plus 1. But we can evaluate that limit, okay? Because this is just a constant part. And this part, 1 over k plus 1, that's going to tend to 0 as k goes to infinity. By the algebra of limits theorem, this would come out as just 1. By the algebra of limits. So for this particular series, it is possible to prove that it's convergent and actually work out the precise values. Okay. So this approach can often be applied to an infinite series sum of am when am is a rational function. A rational function of m. And what is a rational function of m? A rational function of n is a quotient of polynomials. So one polynomial divided by another one. Quotient of polynomials in the variable n. Okay, this one isn't that amazingly complicated because the top polynomial is just the constant 1, and the bottom polynomial is just that quadratic. But in principle, this approach may bear fruit. It may be applicable to series defined by rational functions. Okay, because rational functions have partial fraction expressions. So this behavior of the partial sums may, in some cases, may allow you to determine the actual sum of the series. We called it telescoping. So the telescoping, think of like a pirate's telescope. Yeah, so they're on the boat looking out. Concertina's in and out. When you're using it, you've extended it to the long version. When you want to stow it away, you squash it down, and each part of the cylinder covers the next bit. So that phrase is just meant to describe the cancelling behavior in the partial sum there. For the long part, the long expression for the partial sum kind of telescopes down because each bit is cancelling with its neighbor. Okay, but in other examples, the cancelling is a little bit more involved, and things in general won't cancel with their immediate neighbors. Sometimes they cancel with partners further down the series. So sometimes at the end, you've got many more terms that are remaining. But in the general case, where it's going to work out, the terms that remain, they'll either be fixed constants or terms that converge to 0. So when you apply this limit to the partial sum idea, some of them will go to 0 and disappear, and you'll just be left with the constant terms, which will give you the sum of the series. Okay. Any questions based on that example? So I've got got another example on that, which is taken from a past examination paper. We'll have a look at that now. We just got a few minutes left, so too much time. Okay, so this is taken from the 2014 summer exam. So these two parts made up one full question, which was worth 20% of the exam, pretty much. Yeah. So the first one gives you a series. You're asked to decide whether it converges or diverges, and the second part is another one of these telescoping examples. Okay. Now that first example, it's the question from 2014. So you can see these examination papers if you follow the exam papers link on the Moodle area. Now, because this series contains factorials, the ratio test is a good candidate for a test to try. Okay? So we'll try the ratio test because of the factorials. Because when you put neighboring factorials over one another, you get a lot of cancellation. Okay? You put closely related factorials, divide one by the other, they share a lot of factors. Most of the factors are going to cancel. And if you divide m by m plus 1, that's not too hard to handle as well. So the ratio test says we look at the limit as m goes to infinity of the m plus 1th term. So that will be m plus 1 over m factorial divided by the mth term. If we divide by the mth term, it means we're going to multiply by the reciprocal of the mth term. So what's happening here? Well, all of the factors in m minus 1 factorial are going to cancel out because they all occur here in m factorial. But there's a 1 over m left over. So it's going to be m plus 1 over m squared. Okay. But now we're just taking the limits of that sequence. We want to identify this limit. This is going to be our L, and we're going to base the conclusion about the convergence or divergence of the series based on that. And so the normal technique here is to divide above and below by, well, the highest power of m. Yeah, so this will be 1 over m plus 1 over m squared over 1. And we can recognize what the limit here is using our algebra of limits theorem for sequences. Because the denominator is a constant, so in the limit, the denominator is just going to remain at that constant value. The two parts of the numerator, they're both converging to 0. So in the limit, the numerator is just going to converge to 0. So this just has a limit of 0. That's using the algebra of limits theorem. So this up here was our am plus 1 divided by am, where that's your term am. So because you've got a limit of 0, that's something strictly less than 1. You look at the statement of the ratio test that says that in this case now the series will converge. So the sum of this converges by the ratio test. Look at the second question. So the second question kind of directs you techniques is to use the telescoping behavior of the partial sum here. So to figure this out, we'll need to obtain the partial fraction expansion, partial fractions of 2 over m squared plus 3m. Now, in order to do that, now we'll be doing this in detail soon, but you need to factorize the denominator like that. And then this is going to be something over m plus something over m plus 3. But what we want is the m's to cancel, and for us to be left with just 2. So I think we'll have to do 2 over 3 minus 2 over 3. If you do that, then when you add those two fractions together over the common denominator, the effect of the 2/3 and the minus 2/3 will just be to leave you with a numerator of 2, as it should be. So a partial sum Sk, well, as long as k is bigger than and equal to, let's just be safe, say it's bigger than or equal to 4, although probably 3 will do. You see, how do things cancel here? Each positive term, no, each negative term cancels with a later positive term. Each negative term cancels with a later positive term. But the terms are 3, instead of just being 1 apart, as in the previous example, they're now 3 apart. It's got the m in this denominator and the m plus 3 in that denominator. So Sk, so each negative thing cancels with a later positive thing. That means you're going to have some positive things at the start. So you're going to have 2/3 over 1 plus 2/3 over 2 plus 2/3 over 3. But then everything in the middle is going to cancel, except for the last three negative terms, because they don't have following positive terms. So I think you get minus 2/3 over k plus 1, minus 2/3 over k plus 2, and minus 2/3 over k plus 3. I think that's right. I'm just doing it quickly in my head. Pretty confident about that. I may have slightly miscounted, or slightly, I may need to sit down and just confirm that, but you see what I mean here? So the cancellation is happening 3 steps apart, so you get more stuff left at the start and more stuff left at the end, but the point is that all of these are going to converge to 0. So SK is just going to converge to this number here. We'll call it S. So the sum of the series is going to be S. Okay. Okay, so that's a little bit rushed at the end, but gives us a first look. I think that's maybe the first time we've looked at some examination questions.